Hi, what I have here on the workbench today is an OWON CMS101 clamp meter and oscilloscope combo device. I requested this meter from Banggood for a review. As usual, I will provide a product link in the video description below for those who are interested in getting one after watching this video. On this channel, I have reviewed an OWON CM2100B a while back, and you probably have seen me using that clamp meter quite often in my videos. I actually like that clamp meter a lot, especially the form factor. I will add a card up here if you wanted to check out my review of the CM2100B. Anyway, because I'm pretty happy with the OWON CM2100B, I wanted to see what experience the OWON CMS101 brings. My first impression is that this meter is actually quite massive in size. I didn't realize how big it is until I received the product. You actually can tell its size by looking at the product picture. Here I have a HT208 for comparison, and you can see that this meter is quite a bit larger than HT208. And if I put the OWON CM21B by the side, you'll just see how much larger the CMS101 is. Before I get any further, let's take a look at some of the specifications of this meter. The CMS101 is capable of measuring both AC and DC currents up to 1000 amps in 3 ranges. It supports either auto ranging or manual ranging. It can also measure inrush current, which is important if you wanted to test the power on current draw characteristics of a transformer or a motor. In multimeter mode, it can measure resistance, capacitance, continuity, diode, and frequency. Obviously, we'll do more detailed testing later on. The meter can also be connected to a smartphone via the iMeter app. One of the key selling points is that the CMS101 has an oscilloscope mode. The built-in oscilloscope has a sampling rate of 5 megasamples per second and can measure either voltage or current waveforms. When measuring voltage waveforms, the bandwidth is up to 1 MHz, and when measuring current, the bandwidth is up to 1 kHz. You might think the 1 MHz bandwidth is nothing compared to most of the scopes I have reviewed on this channel. And you are right. Obviously, the intended use here for a clamp meter is to view either the mains voltage waveform or the voltage waveform of a VFD or variable frequency drive, which is usually well below 100 kHz. So the 1 MHz bandwidth for the intended use is actually plenty. Now, how about the 1 kHz current waveform bandwidth? Well, having the ability to observe the current waveform directly from a clamp meter is huge, even with a 1 kHz bandwidth. Obviously, it is not intended to replace your dedicated oscilloscope current probes, but it will be very useful when doing mains current measurements. With the specs out of the way, let's actually power it on and take a deeper dive. The boot up is pretty fast. By the way, did you see the fade-in effect? Let me actually do it again. Watch for the screen here. Let me zoom in a little bit. And you can see the fade-in effect. I don't think I have seen any other instrument doing this. Pretty cool, I guess. If you short press the power button, you will see that you will be able to switch between the meter mode and the oscilloscope mode. Of course, if I press it again, it will switch back to the meter mode. And again, you can see the slide effect. Clearly, OWON had put some efforts into the UI design here. Anyway, the UI design is pretty intuitive. You have 4 of these menu items at the bottom here, and you can interact with them with these 4 function keys. And the tab button here, oh, you can see it. The tab button here, you can see, you switch between the different manual tabs. We have 3 tabs here, and they're pretty well thought out. The first one lets you select the measurement mode. For example, right now we're in DC current measurement mode. You press it again, you go to the AC current measurement mode, so on and so forth. And the second tab, let me tab it again, you can see we have the additional functionalities specific to the current measurement mode. And here we have the min-max, rel, and 0. And the last tab here, that is the same across all measurement modes. That's the system menu. Here we can change the brightness of the display. By the look of it, we have 3 different levels, and you can also change whether or not to enable the auto power off. You can enable it, and you will see this clock icon next to the battery symbol here, and then you can turn it off, of course. By default, I think the wait time is fixed at 10 minutes. And here we have the theme button. You have 2 themes to select from. This is a dark theme. This is a light theme. Now, I'm not sure which one shows better on the screen here. I think they are equally well. Let's keep with the original one. I actually like the default theme. Now, let's start with the current measurement, as that's the primary use case for a clamp meter. For AC and DC current measurement, this meter has 3 ranges as I mentioned earlier, 20 amps, 200 amps, and 1000 amps. And you can either let the meter auto range, or you can manually select the range via the up and down button here. You see that we're changing to manual, and now is 200 amps and 1000 amps, and so on and so forth. You can go down here. And if you want to change it back to auto again, all you want to do is just press the A button. Pretty intuitive. I should note that the frequency bandwidth in current mode for this meter is up to 1 kHz, which should be sufficient for most industrial use. The measurement accuracy of this meter is actually pretty good. Obviously, it depends on the mode and range you are in. In DC measurement mode, for example, it is actually generally at around 0.1%, which is pretty decent. For current measurement mode, it is 2%. Now, because this is a clamp meter, 2% is actually pretty normal for the measurement accuracy. Now let's do some AC current measurement. And here is the setup. On the side I have a Uni-T power supply that's running, and my plan is to use that to draw some load. Of course, we're measuring the primary side, and the power supply is a DC power supply. I'm going to adjust the output so that we can observe the current on the primary side. So now let me hook up the meter here. And there's some residual current here. Actually, we're in the wrong mode here, so let's first change it to correct measurement mode. So let's just measure the current here. And the power supply is on, so we are already reading something. Of course, I'm going to use my Kaiweets HT208D as comparison here. So let me change it to 60 amp measurement mode, and we're going to measure AC current. Let's do it. Let's enable the power supply here. And you can see the two readings are roughly the same, 0.7578 amps. And now let me increase the load a little bit and we'll go ahead again. So let's change the output to parallel. Now we're roughly outputting 30 volts at 10 amps, so let's give it a go. And you can see essentially the reading doubled here. Of course there's some discrepancy, but that is within the range of the specified accuracy for each of the meter. And while we're measuring the current here, you can go to the additional tab, and we can change the display to, let's say, display the frequency here. And you can see, because this is the AC current, we can see that currently the frequency is at 60 Hz. Actually, that's pretty good. You can also see the current as well. Actually, you can see on the Kaiweets, for some reason, we're not seeing the frequency. I don't remember that was ever an issue. But anyway, this video is not about the Kaiweets. It's about this OWON CMS101. So you can see we're clearly able to measure the current frequency here as well. I know you wanted to see the oscilloscope mode, but I think I'm going to finish the other things first, so I'll save that till a little bit later. As I mentioned earlier, this meter is also capable of measuring inrush current in AC mode, which is going to be very useful if you're testing transformers and motor startup characteristics. Let's actually take a look using my electric drill. Let me plug in my drill. Let me change this to inrush mode. And I will change this to inrush mode as well. Okay, so now let's give it a go. It will be a little bit loud. And you can see we're reading 13.99 amps and 13.86 amps. These are actually very comparable readings. Let me change it back to the amp mode so you can see that. Let's do it again. So to do that again, I'm pressing the inrush again. Let's see, yeah, it says inrush. And then I'm going to do this again as well. Ready? And you can see that the measured currents are actually very comparable. In our next test, let's take a look at the DC current measurement mode accuracy. And here is the setup. I'm using my Uni-T meter to measure the output current from my UDP3305S power supply. And currently the power supply is outputting 100 milliamps, and you can see that on the meter here. So I'm going to use my CMS101 to measure the same current as well. And here you can see we have already changed the measurement mode to DC. Of course, I need to zero out the reading here, so let's do that. 0. And let's hook it up to the cable here. You can see we're reading essentially 100 milliamps here. So let me increase the current output here. So let's change it to 1 amp. And you can see we're pretty much reading exactly 1 amp. Let's change it to, let's say, 2 amps. No issues. And of course, because lowest range is 20 amps, essentially we're just in that range only. Let's change it up to 10 amps. That's the maximum I can deliver from my power supply. And you can see that the measurement essentially has no issues at all. So let's dial back down to, let's say, 5 amps. And I want to show you some other functions here. So if you look at here, we have this min max button as well. So by press that, you can see that obviously this is given a measurement interval. So right now the min is 5.04, the max is 5.07. And if we change it, let's see if we can actually impact that reading as well. Yeah, you can see that now I change it to 6 amps. Of course, the max changed to 6 and min still stays at 5. So if it's a time varying signal, you can use that to capture the min and max. So that's pretty useful. And just like any clamp meters, if you move the cable around within the draw opening here, you can see the current actually changes. And that's actually normal. Ideally, you want to make sure that the cable is centered, and that's the maximum accuracy here. And of course, if you move around the cables, you will incur some error. And I think that error is counted in that 2% specification. Now let's take a look at the other multimeter features. Here are the probes supplied. Now these are just your run-of-the-mill probes, nothing special. And I think I pointed out earlier in my other review videos, you can see here the supplied probes are right angled and the jacks are on the side here. Personally, I would prefer if they supplied straight jacks, but other people may have different preference. So let me plug this in and let's check out the DC voltage measurement. Let me switch it to DC mode. And to switch to a different measurement mode, you can just press the button here. So now we're in the DC mode. And by the way, we actually have a dedicated millivolt mode, you can see here. And the resolution for this dedicated 200 millivolt range is actually pretty impressive. It's at 1 microvolt. Now you can also measure AC voltage in the 200 millivolt range as well. Let me press it again, let's see. But for AC measurement in this 200 millivolt mode, you can see that the resolution is only down to 10 microvolts, but it's still pretty decent. Anyway, let's change it to DC 200 millivolt range. And let's take a look here. And right now my standard is outputting roughly 20 millivolts. You can see we're reading 19.995. Essentially we have 20,000 counts resolution here. And of course, if I increase the output to 30 millivolts, obviously you are going to lose 1 digit of resolution here. Now let me dial down the voltage a little bit. And let's see if we can adjust the least significant digit here. So now it's at 0.8. So let me increase it by 1 microvolt. Yeah, you can see that it actually works. So let me increase by another microvolt. Yes, you can see the resolution is actually indeed 1 microvolt. That's excellent. And now let me change it to the volt range. And let's take a look 1 volt at a time. 1, 2, 3. And the update rate is actually pretty decent as well. 4, 5, 6, 7, 8, 9, 10. No problem. And now I have hooked up the input to a variable DC power supply, and let me change the output voltage. And let's see what we got here. Also, I wanted to see how fast the bar graph is updating. So let me change it lower. And you can see the bar graph is actually not updating that fast. It's updating at the same speed as the display. The display update rate is fairly decent at about, I would say, a little bit more than 2 times per second. I'm not sure. You can see that it's not that bad. And the bar graph is not updating any faster than the display here. Of course, now if I change it to the next range, you can see that the bar graph resets. Anyway, that's just a quick test of the display update rate. And by the way, the specification mentioned that this is a 20,000 counts meter, and indeed when we were doing voltage measurement earlier, you saw that was 20,000 counts. But I should mention that that's only for the voltage range. For current measurement mode, it's only a 2,000 counts meter. In fact, when I reviewed the CM2100B from OWON, I remember there were people saying that that meter was actually not a 20,000 counts meter. To OWON's defense, the voltage range does have 20,000 counts, but not the current range. So let me actually show you here. So you can see that right now I'm measuring voltage, and it says 1.9935. That definitely is a 20,000 counts meter. But if you take a look at the current, you'll see that we essentially only have 4 digits here, and the maximum digit can only go up to 2. So in this 2 amp range, it is a 2000 counts meter, which is similar to the CMS101 in current mode. So I wonder if that's a reason OWON removed the 20,000 counts labeling from the CMS101. Anyway, counts and digits don't necessarily apply to all the ranges, which is fairly common across all the multimeter brands, not just OWON. I have recently done a video on this, and you can check it out if you are interested. I will put a link up here if I remember. And let's briefly take a look at the AC voltage measurement. So to change that, I'm going to press this button here, and you can see now we change to AC voltage measurement mode. And let's just take a quick look at the mains voltage. And you can see, actually it's a nice touch. You do see this warning here indicating that's high voltage. And I think according to the manual, that voltage sign started showing around 42 volts. Let's actually use a variac and let's verify that. And while we're at it, I also added a unity meter to monitor the output voltage so we can see the accuracy here. Anyway, let me increase the output. The update rate is pretty fast. Okay, so I think it's actually roughly 30 volts instead of 40 volts. You can see that as soon as we exceeded 30 volts, we start seeing this warning message here. And the reading largely agrees with what we have on the unity here. Alright, now let's measure a couple of resistors. Let me change it to resistance measurement mode. And let's short the leads. We have some residual reading, but as I mentioned earlier, you can tab it here, and you can press rel to rel it out. So let's actually measure a precision resistor. This one is a 100 ohm resistor, and you can see that we're pretty much measuring exact 100 ohm, so no problem. Now, these leads are not gold plated, so the contact resistance is not consistent. Now let's measure a 1.25K resistor, that is 1% tolerance. Oh, by the way, the rel mode only works up to 200 ohms, so let's cancel that. You can see that the alternating speed is not the fastest, but it definitely gets the job done, and the result is quite accurate. Let's try a few more resistors. That's a 1K resistor. And let's try another one. That's a 4.7K resistor. And just for good measures, let's try a 1 mega ohm resistor. Yeah, no problem. Alright, now let's take a look at the diode mode. And I think that's continuity mode. Let's actually try that first. Yeah, it's latched. It's a little bit on the slower side, especially the display. You can see that there is a 1 second delay, but the beeper definitely is pretty fast. Now the diode mode. And for diode measurement, I'm going to go straight to a white LED. And let's take a look at the voltage drop to see if it is able to measure that. Yeah, you can see we have no problem lighting up the LED, and also we can measure the voltage drop at 2.6 volts. No problem. Okay, let's take a look at capacitance. For capacitance measurement, of course, we also have the rel functionality here. So let's rel it out. And let's take a look at a very small capacitance. Here I have a 22 picofarads capacitor. Let's take a look. And of course, it can be pretty difficult to measure that. Yeah, you can see, okay, we're roughly in the ballpark, and that means you definitely can use this to measure small capacitors, and you can see we're able to measure the capacitor here with no problem. Now let's just go directly to a large capacitor here. This one is 15,000 microfarads. Let's give it a go. Yep, no problem. Let's see what else we got. We can also measure frequency, and let's actually do that first. According to the manual, the maximum frequency it can measure is 20 MHz. And you can see right now we're inputting a 19.999 MHz frequency, and it can measure that with no problem. And the OWON also supports non-contact voltage detection, the NCV. So let's take a look at here. And you can see that here's a live wire, and it detected it with no problem. Alright, now let's take a look at the oscilloscope mode. To switch to oscilloscope mode, we just need to press the power button again. And by default, it is actually in current mode. Let's actually switch to the voltage mode first, as we still have these leads attached here. So that's our voltage mode. Right now is 30 millivolts per division. Let me actually zoom in, we can see it better. Of course, right now it is picking up something. I suspect it's because we have this 30 millivolts per division sensitivity here. And if I short the leads, you can see here. Yep, we're not seeing anything. That's good. Actually, without anything connected, let me use the auto acquire to see what we're picking up here. Yeah, you can see we're just picking up some mains interference here. That's from the environment. Let's actually measure the mains waveform, since we have a power strip back here. So let me do that. You can see here's a power strip. I'm going to put the probes in. And of course, we're now in an overrange situation. And let's actually press the auto button to acquire that signal. The reason it's showing only 300 millivolts per division is because I haven't turned on the power strip yet. So let me do that. Of course, right now it overranged. This time actually, let me show you how to adjust the range manually. So, you can see that. I'm going to press the button here. I think it's this one. No, this is for time. And it's up and down. Yeah, 1 volt, 3 volts, 10 volts, 30 volts per division, 100 volts per division. And now you can see we get a proper sinusoidal that is essentially from the mains. And of course, you have some of the secondary displays. You can see we have the peak-to-peak voltage here, and we have the min and max. So let's actually take a look to see if there are other options we have in this oscilloscope mode. So for that, I'm pressing this tab. Let's see here. You can change the triggering edge. So let's see, falling edge, rising edge, and I suppose this is for changing the, this is changing the trigger position. Very good. So you can see, although we don't have a lot of functionality here, but it's actually quite intuitive and useful. So now let's measure a few standard waveforms and see how this oscilloscope mode behaves. And now I'm outputting a 1 kHz sinusoidal from my signal generator, and currently the amplitude is at 5 volts peak to peak. You can see that we're displaying this with no problem. So let me actually increase the frequency here. So let's do 10 kHz. And of course, we have to change the time scale. And 10 kHz, no problem. Let's do 100 kHz. You can see that still no problem. By the way, the oscilloscope is really easy to use here. And you can see that we can adjust the amplitude and the time base here. So let's actually change it to 500 kHz. Still no issue. Now the question is, can we do 1 MHz? Let's do that. So let me expand this. Looks like this is the fastest horizontal at 2.5 microseconds per division. Let's increase 600, 7, 8, 9. Yeah, it's okay. I mean, you can still see that we get this 1 MHz, and the peak to peak right now dropped to 3.8 volts, and we're sending out 5 volts, so that roughly is the 3 dB bandwidth. And for an advertised 1 MHz bandwidth, this is actually not bad at all. This is pretty much what we should be expecting. And here we have a 100 kHz square wave. You can see that, no problem. And let's change it to, let's say, a ramp signal. And let's display an arbitrary waveform here. Here is the absolute value of a sine waveform, no problem. And let's see what else we can try. You can see that we're actually able to display these waveforms with no problem at all. So I would say this is actually a pretty good oscilloscope, of course, realizing that it is only up to 1 MHz. But for what it is, it's actually working pretty well. And remember the positioning of this meter. For the 1 MHz bandwidth, that should be sufficient for most of the industrial applications. And now let's take a look at using the oscilloscope mode to observe current waveform. This is actually very useful in my opinion, as typically to observe the current waveform, you would need a current probe and an oscilloscope. And the setup can be quite clumsy. Sometimes you just need to get a ballpark before doing any in-depth measurements, and this is where the CMS101 comes in handy. So let's give it a go. To change to the current mode, let's press this F1. And now you can see we changed to current measurement. The sensitivity in current mode is actually not that high here. As you can see, we are at 10 amps per division, and that's the highest sensitivity, as the next level is 30 amps, 100 amps, so on and so forth. So let's go to the highest one, which is 10 amps per division. That's the highest sensitivity. And let me set this up. You can see that I'm measuring the input current into the power strip, and connected to the power strip is my UDP3305S. That's the power supply. And I'm going to short the output and try to draw 10 amps on the secondary. So let's see what the waveform we're seeing here. Alright, now let me enable the power supply output. And by the way, the power supply only can draw 300 watts, so the actual current on the primary is only going to be 3 amps, so which will be tiny on this oscilloscope, as currently we're at 10 amps per division. So let's give it a try. Currently it's at 2.5 microseconds per division, and that's too low. Let's change it higher. And now you can see the input waveform at 10 milliseconds per division. Let me zoom it in a little bit more. And the waveform you're seeing here, although the amplitude is not that great, that's actually a classic current waveform into a full bridge rectifier. Now I have changed it to a heavier load, that's a ceramic heater, and let's power it on and take a look. And now you can see we can see this waveform a lot better because we're drawing 8 amps. As we have demonstrated, the oscilloscope mode on this OWON CMS101 is quite useful, as it supports both voltage and current waveform measurements. The only thing missing in my opinion is the single-shot triggering capability. And if you take a look at the triggering manual, you'll see that we can support rising edge, falling edge, and then we can adjust the triggering level here. And that's about it. Now I do wish OWON can add the single shot capability. It will be very useful when measuring the inrush current waveform. Without single shot triggering, you unfortunately cannot use the oscilloscope mode for measuring inrush current. Just like the CM2100B I reviewed a while ago, the CMS101 can also be connected to your smartphone via the iMeter app. So let me demonstrate here. To do that, we need to enable the Bluetooth here. And to enable the Bluetooth, we just press and hold the tab button here. And you can see that we have this symbol here showing that the Bluetooth is on. So let me turn on the iMeter app. Right now nothing's connected. Let's add a device. And you can see we have this BDM. That's actually this meter. So let's try to connect. And you can see once we connect it, we are essentially getting the same reading as what we see on the meter here. So let me actually, let's see, how do we get rid of the glare here? This is probably good enough. Now let me ramp up the power supply current and we'll see what we get here. And let's do 1 amp, 2 amps, and you can see we have this synchronized display on the smartphone. Another benefit is you can actually use the charting capability here. So let's go to the data chart. And now you can see the graph is being updated based on the measurement here. So let's increase the current 3, 4, 5, and we run back down. 4, 3, 2, 1. And you can see that everything is being captured on this display here. So that's a very useful feature for data logging. Alright, time for us to open it up and take a look inside. The meter uses a single 18650 cell, and the supplied one has a 2.6 amp hour capacity. So let's actually take a look at how much the current draw is and get a feel of how long the battery would last. So you can see here is the battery, 3.7 volts, 2600 milliamp hour. Right now I'm using an external power supply to supply the 4.2 volts input voltage and using my unity meter to measure the standby current. You can see here, this is a setup, and we're only reading about 5.1 microamp, so that's excellent. So now let's take a look at how much current it draws during operation. And for that I'm going to change it to amp range, just in case. Alright, power it on. And we're actually not drawing much current. We're only drawing about 100 milliamps or so, and actually less than that. So actually let's change to oscilloscope mode. Again, we're drawing similar amount of current. So that's actually not bad. Let's actually change, let's say we change the display brightness. And you can see in the dimness setting, actually we're only drawing less than 60 milliamps. So that's actually excellent. And it appears that the display does draw most of the current. You can see here, we are increasing to the brightest. Now we're drawing 100 milliamps. And even at 100 milliamps, a 2600 milliamp hour battery would last you more than a day continuously. So the battery life of this meter is actually very good. And there are just a few screws securing the case. After opening it up, you can see that the board layout is actually very clean. Let me zoom it in a little bit so you can see it better here. You can see towards the left we have the current clamp sensor that is connected to the board here, and we have 3 of these trim pots, and those are used for calibrating the current sensor. And here we have the current sensor amplification circuitry that is centered around a op-amp. The op-amp part number is 02338. And moving towards the right, we have our main microcontroller, that's HC32F460, which is an STM32 variant. It's an ARM Cortex M4 MCU. And this chip is made by HDSC. And let me move it to the right a little bit more. Up here would be our digital multimeter section. The dead giveaway is this chip here, that's a LM385-1, which is a voltage reference for the digital multimeter. Unfortunately, the marking on this DMM chip has been etched off, so we don't know exactly which chip they're using, but nevertheless, that's our multimeter chipset. Up here we have this relay for switching the input, and we also have this chunky PTC resistor for protecting the input. But I don't see any MOSFETs on this side, and I don't think there's any MOSFETs on the other side because we don't have any footprints here. From this image you can kind of see the high voltage input voltage divider here that is formed by these resistors. And if we move down, we can see we also have this SGM4056-6. That is our power management and charging chip. And here we have a couple of headers by the look of it. This one is probably for programming the STM32, and these are probably 2 headers, I'm guessing, because you have 2 of these grounds, and these are probably the UART ports. Overall, I have to say the construction is excellent. Well, that pretty much concludes this video. In my opinion, this is an excellent clamp meter, and the built-in oscilloscope is actually very useful. I'm sure you will see me using this meter in future videos. Anyway, I hope you enjoyed this review and teardown. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.